Thank you very much for this invitation. I am very happy to give this lecture. I visited your university in 2020, so that was 3 years ago, just before the pandemic, and I keep a very fond memory of my visit there. It was a very nice experience, and I am glad to participate again to your activities. So just one moment, I will put my screen.
Okay, please.
I will put my screen in big size. Okay. Yeah, it will be better for me. So, is it okay that we start now? I will. Yeah.
Yes. Actually, it's already the time, but some of them maybe because in Indonesia, for Islamic praying,
okay.
Sometimes it is because the praying time is depend on the sun. So I think they will join immediately. So it should be okay if we want to start because some online participant is already here. So I think it should be fine in general.
So, do you prefer that I start now or later?
Yes, please. Now. Yeah.
Okay. So, and you tell me if you prefer that I stop. When you wish that I stop, you tell me.
Yeah. Okay.
I am going to speak on analytic number theory. The main goal of my lectures and of all the topics which I will describe is to study the sequence of prime numbers. So we have the sequence of prime numbers, which is 2, 3, 5, 7, 11. So let me say that this is P1, P2, P3. And we have the prime number Pn. And one of the main problems during several centuries was to study the behavior of Pn. And what is called the prime number theorem, which is called PNT, the prime number theorem, which was proved by Hadamard and de la Vallée-Poussin, but which was the main conjecture for a long time, is to prove that the number Pn varies like n log n, which means that the quotient Pn divided by n log n tends to 1 when n tends to infinity. So this is one way of stating the prime number theorem. There is another way which is equivalent, and it's an exercise to go from one version to the other one, which is to count the number of prime numbers which are less than a given bound. So let me define phi of x as the number of p, where p is prime, and p is less than or equal to x, when x is a real number. And the prime number theorem is equivalent to say that phi of x is equivalent to x divided by log x, which means that the quotient of phi of x with x over log x tends to 1 when n tends to infinity. The main tool to study this sequence of prime numbers is analytic number theory, which was essentially introduced in this topic by Euler. And so Euler studied the sequence of prime numbers by looking at what is called the Riemann zeta function. So this Riemann zeta function is defined as a sum for n greater than or equal to 1 of 1 over n to the s. So n runs over the set of positive integers greater than or equal to 1. And what is s? When Euler introduced this function, s was a real number. It's still okay if I write here?
Yeah, we can still read it.
Okay, this is the limit.
Yeah, that's the limit, correct.
And now, if S is a real number, we want zeta of S to be a convergent series. And it is elementary calculus that this is a convergent series for S greater than 1. Euler also studied the values of zeta of S when S is a negative integer. And the formula which is here is not true in the sense that the series is not convergent. But the main improvement on the work of Euler was done by Riemann, and this is why this is called the Riemann zeta function, when Riemann studied this function for S in C. Now, if we want to have a convergent series, absolutely convergent series, we have to make some assumption on S, and we have to look at n to the S, if S is a complex number. And n to the S, by definition, is the exponential of S logarithm of n. And I will discuss a little bit more the logarithm, but here n is a positive real number, even an integer. And so this is the usual logarithm of n. And now when we look at the modulus of n to the S, which is a complex number, this is exponential, the real part of S times log n. And if we want the series to converge absolutely, the condition on S is that the real part of S is greater than 1. Riemann published a single paper in 1859 on number theory. And this paper is a very fundamental paper, which was the source of a lot of work after that. And in this paper, Riemann proved several results about the Riemann zeta function, which was not called the Riemann zeta function at that time. And I will discuss a little bit the achievements of Riemann and the modern improvements which have been done, including the Riemann hypothesis, which is one of the most important open problems nowadays in mathematics and including number theory. So what was the first result of Euler on this Riemann zeta function? Say S greater than 1, a real number. The first result is the so-called Euler product formula. And the Euler product formula is the following. And this Euler product formula explains why this zeta function is very useful to study prime numbers. So Euler product formula. It is that this series, sum of n to the s, is equal to the product of the p. P denotes the set of prime numbers of 1 minus 1 over p to the s to the minus 1. I will explain the meaning of this symbol, the product. But I will start by proving the following fact. The first step is to prove that the series which is here, so I did not write it, but I take S to start with. I take a real number which is greater than 1. And then we will see what happens if it is a complex number. It does not make too much difference. So the proof is that, the first part of the proof is to prove that the sum of 1 over n to the s, which is the zeta of s, is equal to the limit as, say, capital P tends to infinity. And we take the prime numbers P, which are less than or equal to P. This is capital P, this is small p. And then we take the product for P. We take the limit, the limit when P tends to infinity of the product for P greater than capital P and P prime of 1 minus 1 over P to the S to the minus 1. This is a finite product, so you know what it means. And we have a finite product depending on capital P, and we take the limit as capital P tends to infinity. So this is the first step. So let us start with this step. And the proof runs as follows. We have 1 over 1 minus x, and this is a formula which we do quite often, which is the sum for, say, n greater than or equal to 1 to 0 of x to the n. So it is 1 plus x squared, and so on. And so the x which we have here is 1 over p to the s. So we take x equal p to the minus s. And we have to make a product. So we write this product by taking p equal to 3, 5, and so on. So the finite product, which is here, the product for p less than or equal to capital P of 1 minus p to the minus s to the minus 1, which is this product here. What is it? It is a product, so we start with p equal to. It is 1 minus 2 to the minus s minus 1, 1 minus 3 to the minus s minus 1, 1 minus, so let us say that p is a prime number. The last element is p minus s minus 1. So it's just this finite product. Now we replace x in this formula by 2 to the minus s, 3 to the minus s, and so on. So what is this product? It is 1 plus 2 to the minus s plus 2 to the minus 2s. This is the first term. The next term is 1 plus 3 to the minus s plus 3 to the minus 2s. And the last one is 1 plus p to the minus s plus p to the minus 2s plus and so on. And we have infinite series at each time, which are from here. But this formula is valid if x is less than 1. And here, x is p to the minus s. It is less than 1. S is greater than 1 and is a prime at least 2. So we have a finite product of infinite series, but we expand it. We will have 1, and then we will have a sum. So this will be equal to the sum of. So we extend this. We develop by taking just the multiplication, and we have n to the minus s. But what are the n that we have here? We have all the integers n, which have all the prime factors less than capital P. So it's n belongs to a certain set E of P. And what is the set E of P? It is a set of integers such that the greatest prime factor of n is less than or equal to capital P. Okay, so this is the finite product. And you see that when capital P tends to infinity, this series will converge to the sum for n to the minus s for all this n, because we have all the integers which have all the prime factors less than p, and this is for all p. So this is the first part of the proof. Now for the second part of the proof, I have to give a definition of what is an infinite product. And this is not as obvious as we can believe. And before going to the second part of the proof, I would like to remind a few facts about the logarithm of complex numbers. We use the logarithm, where was that? It was somewhere. We had the logarithm, and I told you, we just take the usual logarithm when we have an integer which is greater than 1. But we will need the logarithm for complex numbers. And so I wish to remind you of what is the logarithm, because it's important to know exactly what we are doing. And infinite products like this one will occur during this course many times in many different situations. Okay, so I remove that, and then we will come back to the proof. So I come back to the complex logarithm. You know the real logarithm. It is the inverse map of the exponential map. So you have the map from R to the positive non-zero numbers. So this is the x gives, say, z, t gives exponential of t. So R plus star mean the positive real numbers, which are strictly positive. And you know that this map is surjective homomorphism from the additive group of R to the multiplicative group of the positive real numbers. The logarithm, the usual logarithm, is a bijective map which goes in the other direction. So this is bijective. So the usual logarithm goes from R positive, say, to R, and it is a map which maps, say, U to logarithm of U. So this is the usual logarithm. And by definition, the exponential of logarithm of U is U, when U is a positive real number. By the way, I use the notation e to the t, and it is the same as exponential of t. I will use one or the other. It does not matter. So this is the classical logarithm. And we have the derivative of the exponential function, exponential t prime equal exponential of t. And because of that, the derivative of log u is 1 over u. I considered before the expansion of 1 over 1 minus t, and we can take u equal 1 minus t. And then we have the exponential, the expansion of this function 1 over 1 minus t. We have the derivative of log u. We know that the logarithm of 1 is equal to 0. And because of that, we have the formula, which is logarithm of 1 minus t equal minus t squared over 2 minus t cubed over 3 plus and so on. And this is valid when t is less than 1. Yes, t is less than 1, so 1 minus t is between 0 and 2. In fact, this formula is valid also for t equal minus 1. And we will come back to that later. if you take t equal -1, this series is not absolutely convergent, but it is convergent, conditionally convergent, and we have the formula which is important for the course, which is log2 equal 1 minus 1 over 2 plus 1 over 3, and so on. So this will be useful later. Okay, so this is the real logarithm that you know well, but I want to speak on the complex logarithm. And for that, it is natural to look at the map from C to C star, which maps Z to exponential of Z. So this is the exponential function, complex exponential function. It is surjective. It is a homomorphism from the additive group of C to the multiplicative group of C star. But there is a kernel, and the kernel of X is a set of Z, so that exponential of Z is 1, because this is the additive group, this is multiplicative group. And as you know, this is Z 2 pi I. This is a set of multiples of the number 2 pi I. This may be taken as a definition of the pi. And therefore, we have an isomorphism between C over 2 pi I Z and C star. So this is an isomorphism. And now, if we want to take the logarithm of a non-zero complex number, the number should be non-zero because otherwise it's not defined. If we want to take the logarithm, we have not a single number log Z, but we have a class modulo 2 pi I Z. And to any logarithm, we may add some multiple of 2 pi I. So I will use the following definition. When I have a number W, a non-zero number, we will say that Z is a complex value of the logarithm of W if exponential of Z is equal to W. And so, because this is surjective, any number has a logarithm, and it has infinitely many logarithms. If Z is a logarithm of W, then we have infinitely many logarithms of W, which are the set of Z plus 2 pi I times a number K, or K in Z. So this is the set of complex logarithms. It's probably something that you know very well, but I prefer to be precise on this because there should be no ambiguity in the rest of the course on this topic. So we have infinitely many logarithms. If we use the notation log Z, we have to say which logarithm we take, but there is a particular value which is quite natural, which is if you have a number which is close to 1, if W1, W minus 1, say I will take U less than 1, so I take a complex number less than 1, I can take a logarithm of U, of 1 plus U, which is given by the series. So it was minus 1 over U, okay, so, minus U square over 2, minus U cube over 3, minus 8, and so on, is a logarithm. First of all, it is convergent as a series of complex numbers, and it is a logarithm of 1 minus U. So sometimes it will be convenient to write logarithm of 1 minus u by saying that this is the principal value of the logarithm. So if you want a picture, we have the point 1, which is here. Here we have 0. Here we have 2. And here we have the point 1 minus u, which is in this disk. U is close to it's close to 0, which is less than 1. Okay. And so in this region, we have the principal value of the logarithm. We can extend this principal value by removing the negative line, real part of z of u less than 1, and on this open set, the set D, we call the set of u of 1 plus u, or the set of w, which are not negative. So this is the set of complex numbers where you remove the negative axis. Then the principal value of the logarithm extends to an analytic function. The principal value of the complex logarithm it is not defined by this series. This series is convergent only here, but it is the only analytic function which has the property that the imaginary part is between 0 and 2 pi. So z, the real part, the imaginary part of z, is between 0 and 2 pi. Oh, no, minus pi and 2 pi. Minus pi and pi. Here the imaginary part is 0, and so this is minus pi and plus pi. We can extend it by taking one of the two strict inequalities less than or equal instead of strictly less, but then it's not analytic on this closed set. This is why I take an open set. Okay, so this is what I wanted to say on the complex logarithm, and I suppose that this was not new for you. Now I wish to define infinite products. And I will need the complex logarithm. Infinite products. Of complex numbers. So we have a sequence of complex numbers, say Zn. So it's Z1, Z2, Zn. And I want to define what is the convergence of the infinite product, which is the product for I equal 1 up to infinity of Zi. What does it mean that this infinite product is convergent? So this is the product Z1, Z2, Zn, and so on. There is a naive way of defining this, which is to say that the limit, if you take a finite product has a limit. And so we will say is convergent if, so this is the definition. So if first the limit as n tends to infinity of Z1, Zn exist. So this is a sequence of complex numbers, Z1, Zn, the product. and we want that this sequence has a limit. So this is the third condition. But it's not sufficient for several reasons. First of all, if one of the Zi is 0, then the product, the sequence of products converges to 0, because as soon as we have one element which is 0, the product becomes 0. So there is a problem with one of the Z which is 0, but there is another problem, which is that when we have a product, we want that a product is 0 if and only if one of the elements is 0. And it may be that this limit has a limit, this limit is 0, and no of the Zi is 0. Let me just give one example, and you can check what I claim later. If you take 1 minus 1 over n, if you take this for Zn, or 1 over I, this is Zi, you may check that Z1, Zn tends to 0. Well, okay, I put I plus 1 just because if you take I equal 1, you would get Z1 equals 0. So I take this one, 1 minus 1 over I plus 1. So the first one is 1 minus 1/2, and then 1 minus 1/3, and so on. And you may check that the limit is 0, and none of these numbers is 0. So this is a bit annoying, and so the condition is the following. The condition is that, the second condition, which is part of the definition, is that only finitely many of the Zi are 0. And also that if some of the Zi is 0, the limit exists and it's 0. But we want also that if Zi is different from 0 for I greater than n0, we want also that the limit as n tends to infinity of Zn0, Zn0 plus 1 up to Zn, we request that this limit exists and is not 0. So this is the limit of numbers which are not 0, and we want that the limit is not 0. This is the definition of a convergent infinite product. And I will come back to the example that I started with the Riemann zeta function. But before that, I want to make some comments on this. We have this limit which exists and is not 0. So if you define, say, Qn equal Zn0, Zn0 plus 1, Zn, and if you look at Qn plus 1 over Qn, this number is not 0 because Zi is non-zero for I greater than n0. So if you look at Qn plus 1 over Qn, this is just Zn. Qn plus 1 and Qn has a limit, and the limit is the same. So Zn tends to 1. So if you have an infinite product which is convergent, all the sequence of Zn tends to 1, and therefore only finitely many are not 0. We come back to this condition. So this is why for the infinite product, we will often write Zn equal 1 plus un, and we will consider the product for I equal 0 to infinity of Zn. We will write it as the product of 1 plus un. Okay, so I should choose the letter. and it is not 0, but it is 1. So instead of Zn, we write 1 plus un. It is tempting to use what I said about the logarithm and to take the logarithm. When we have a product, it's natural to take the logarithm. Because of what is written here, we see that un tends to 1, to 0. Zn tends to 1, and so un tends to 0. And so we can take the principal logarithm of 1 plus un, at least if n is sufficiently large. Maybe a little bit larger than n0, but sufficiently large. And so we can look at we have the first part, which is the finite product, and then we have the tail. And so we can assume that for n greater than or equal to capital N, we may assume that un is less than 1, because un tends to 0. And so we can look at the product for n equal capital N to infinity. Well, we can start with the capital M of 1 plus 2n. When we have a finite product, we can take the logarithm of this. And this logarithm is the sum for n equal capital N to capital M of the logarithm of 1 plus un. And un tends to 0. So the logarithm of 1 plus un is equivalent to un. And so you see that we have a connection between the convergence of the series of the product and the convergence of the series of un. So an important auxiliary lemma is the following. And this lemma will be useful to consider the absolute convergence of an infinite product, which means that we will replace the un by the modulus of un in this series here. So assume that the un are positive real numbers, then there is some question? No? Okay. So then the product, which is here, is convergent. Okay, 1 plus 2n is convergent if and only if the sum of the un is convergent. The proof, I thought I could give the proof, but I should go further to some more important results. But the proof is rather elementary using the logarithm. And maybe I give just one element for the proof, which is okay. It's just to write the series which is here, and to write precisely that the log of 1 plus un is equivalent to un. Because of this lemma, we deduce that if the product of 1 plus modulus of un is convergent, which means that the sum of the modulus of un is convergent, then the product of 1 plus un is convergent. So this is a definition of absolute convergent product. Which is a product of 1 plus un, which has the property that the product of 1 plus modulus of un is convergent. This follows from the lemma. And I insist on that because there is some mistake that some students make often, which is to forget the assumption that un is positive. So I give you some exercise to check that this is necessary. So exercise. So I remove the condition that un is positive. And then we can have an example where this is convergent and not this one, and conversely. So give examples of sequences UN of complex numbers, such that, so the first example A is that the product is convergent, and the series of UN is a divergent series. And the second part of the exercise is the product is divergent, product of 1 plus UN. Well, a divergent series, you know the definition. A divergent product, I did not give a definition, so I will just say is not convergent. And the series is convergent. Okay, so this is an exercise. If you do not find the solution, you will ask me tomorrow when I start the course. But I am convinced that some of you will find one solution. There are many solutions for that. And then the one who finds the solution will explain to the other ones. Okay, so this is what I wanted to remind you about infinite product. There is one example of infinite product which will occur in this theory, which is the Weierstrass factorization theorem. So the Weierstrass product. The problem of the Weierstrass infinite product is the following. You give a sequence of complex numbers, and you want to find a function which has exactly this sequence of numbers as zeros with given multiplicities. So you have a sequence of complex numbers, and you want to find a function which is an entire function in C, so that the zeros of f are exactly the point Zn. Exactly, there is no other zero. So, of course, there are some conditions on Zn. What do you know on the zeros of an entire function? We have a sequence of numbers, and so the function has a set of zeros, which is a sequence, so it's countable, and so the function is not the zero function. And so we have an entire function which is not zero. The set of zeros is a discrete set. So this is the first condition, which means that if you take one Zn, there is a neighborhood of this Zn, so that there is no other zero of f in this neighborhood apart from Zn. So this is what is called a discrete set. So the assumption is that we have a sequence of numbers which give us discrete set. And then the Weierstrass theorem is that there exists an entire function in C, so that the set of zeros is the set Zn, and we want to include multiplicities, which means that we can repeat some Zn finitely many often. Finitely many because it's a discrete set. But this is the condition. So for each Z0, there is only a finite set of n's so that Zn equal this number. So how does Weierstrass solve this problem? A naive way would be to say I take Z minus Zn, and I take the product of Z minus Zn. This will not work because Zn tends to infinity. So this will not work. So Zn tends to infinity. So a better idea is to take 1 minus Z over Zn. Of course, we need Zn different from 0, but there is only finitely many n so that Zn is equal to 0. So we take the n, we take a power of z, z to the k, times the product for n greater than or equal to 1 of 1 minus z over zn. This is a better idea. We have k. So it's the zn which are different from 0. We have 0, which is counted with the multiplicity, which is the number of n, so that zn equals 0. And we have a product, and this product vanishes exactly when z is equal to zn with the multiplicity. The problem is that, in general, this product is not convergent. We will see some example where this product is convergent, and then we have the one solution. If we want to have all the solutions, we multiply by a function which has no zero. And you may know that an entire function which has no zero is a function of the form exponential of g of z, where g is analytic. An entire function in C. So this is a typical example of a function which has no zero. And now we have this product, but this product usually does not converge. And so the idea of Weierstrass is to multiply by a function which does not vanish, and so that we will not change the set of zeros. And we will multiply by a function which depends on the Zn in such a way that this product is very close to 1. What is the natural choice? It would be to take the logarithm of 1 minus z over Zn. This would be natural because you multiply u by exponential of u minus u, and you get 1. But this is not an analytic function, but what we do is that what we do is that we multiply by an approximation of this function, and an approximation is given by the infinite product. So we take just a finite product, which is exponential z. So we remove that, and instead of that, we write exponential z over zn plus z over zn square times 1/2 plus 1 over kn. Okay, maybe I should write it more on the left. Exponential z over zn with 1/2 z over zn square plus 1 over kn z over zn kn. And we choose kn in such a way, so it's finite, it depends on n. We choose kn in such a way that this infinite product converges, and it's easy to see that there is always a choice of kn for which it works. And in the condition that, in the situation that we will see, kn will be usually 0, 1, or 2. So it's quite easy. Okay, that's all. And now I come back to the theorem of Euler on the convergence of the infinite product. And what I said is that the sum for n greater than or equal to 1 of 1 over n to the s is equal to the infinite product for p less than capital P, for p prime of 1 over 1 minus 1 over p to the s. This was the formula which I gave at the beginning. I already proved that if you take a finite set of prime, then if you take capital P, which tends to infinity, and if you take the primes less than P, then the limit exists, and in this one. But this is not sufficient for the definition of infinite product. What we need to prove is that the product is convergent. None of the terms is 0. So what we have to prove is that the limit exists and is not 0. So we are interested in the limits as p tends to infinity of 1 of the product of p level to p of 1 minus p to the minus s to the minus 1, and to prove that this is non-zero. So we have s, which is a real number which is greater than 1, p is at least 2, and so p to the minus s is less than 1, and so we can take the logarithm of this quantity. So we can take the logarithm of a finite product, and it is a p less than p of 1 minus p to the minus s minus 1. And okay, so we want to check that this has the limit that we expect. So we have to look at the of 1 minus p to the minus s. P to the minus s is sufficiently small so that we can take the formula, which is that this is the sum for m greater than or equal to 1. We have the sign minus, and it's a p to the minus ms divided by m. This is the expansion of the logarithm that we have seen later in the before. And so what we obtain is that zeta of s is the exponential by taking the limit of the sum of the p, the sum over m greater than or equal to 1, of 1 over m p to the ms. So zeta of s is the exponential of a complex number, and this complex number is well defined. This series is convergent. If you take s real, it's a sequence, it's a series of positive real numbers. If you take s complex, then the modulus is convergent. And therefore, this proves that zeta of s is different from 0 for the real part of s greater than 1, because it's the exponential of a complex number. We have written zeta of s as the exponential of a number. This means that this number, the double sum here, is a logarithm of zeta of s. So we can write log of zeta of s is equal to the sum for p, sum for m, of 1 over m to the ms. This means that this function has a value which is 1 logarithm of zeta of s. So this function defines an analytic function in the half-plane real part of s greater than 1. And it is this is analytics in this real part, and the exponential of this function is zeta of s. And so this completes the proof of the convergence of the product. There is one way to write this result, which is to define the so-called von Mangold function. Which is the function which is defined for n greater than or equal to 1, and it is defined by lambda of n equal log p, if n is the power of p, and 0 if n is not the power of a prime. Of a prime number. So if we take this definition here, you see that the result which is here will give something if we take the logarithmic derivative. So the corollary is that zeta prime of S divided by zeta of S, it's the derivative of the left-hand side, and so it is minus the sum for n greater than or equal to 1 of lambda of n divided by n to the s. Okay, so it was a bit long, but I wanted to be very clear on this initial step in the study of the Riemann zeta function. So the next step is to extend this function to see how to extend it as a function which the first remark that we can make is the fact that if we take S which tends to 1, S greater than 1 but tends to 1, the left-hand side becomes the harmonic series, and the harmonic series is divergent for S equal 1, and therefore the infinite product is divergent for S greater than or equal to 1, for S equal 1. And so if we use the divergence of the harmonic series, which is the harmonic series, if you look at this series, it tends to infinity when n tends to infinity. This proves that for S equal 1, this infinite product is not convergent. And therefore, when you look at the series sum of 1 over P prime, this series is a divergent series because of what I proved before. You take S equal 1 and you have the equivalence between the convergence of the product of 1 minus 1 over P and the convergence of the series sum of the P. P is positive. And so we get some information on the distribution of prime numbers, which is not obvious. It's not only that there are infinitely many prime numbers, but that there are more prime numbers, for example, than squares, because the sum of 1 over n squared is convergent. And this is something which is not obvious, and you see that the analytic method gives the proof quite easily. We need the divergence of the sum of 1 over n. So let me expand a little bit this topic. There are several proofs of the divergence of this series, but one of the early proofs which I like is due to Nicolas Oresme, who was living in the 14th century. And the proof of the divergence of the series is the following. You start by writing the series. There are several proofs, but one of them is the one that he gave was the following. You look at S equal 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, 1 over 5, 6, 7. And you group the elements as follows. If you take 1/3 plus 1, 4, you get 1 over 8. If you take 1/3 plus 1, 4, you have two elements which are greater than 1, 4. And so this is greater than 1/2. If you take the elements which are here, you have 4 elements which are all at least 1 over 8, greater than 1 over 8. And so this is greater than 1/2. And if you continue like this, you see that you have infinitely many subsums greater than 1/2, and therefore the sum is infinite. This proof enables you to get the following result. If you define Hn as 1 plus 1 over 2 plus 1 over n, if you expand this proof, you will get the fact that log n divided by 2 log 2 is less than Hn and less than log n divided by log 2. I wanted to give the proof. It's just elementary using this sketch of proof, but I think it's better that I continue now. So this is a proof of the divergence of the series. There are several other proofs, and one of them works as follows. It is a short proof. You defined S0 equal S over 2. And so it is, you divide by 2. So you start with 1/2, 1 over 4, 1 over 6, and so on. So you see that you have half of the terms which are here. And if you take the difference between, so you define S1 equal S minus S0, you remove the elements which are here. So you have the inverse of the odd numbers. 1 plus 1/3 plus 1 over 5. But S is 2S0 because of this. So S minus S0 is S0. You see immediately that there is something which is not going nicely, because if you compare S0 and S, you see immediately that S1 should be greater than S0. But if you take S1 minus S0, you get 1 minus 1/2 plus 1/3 minus 1/4 plus and so on. And you have an infinite sum of positive numbers. So this is greater than 0. So this is a contradiction with what was done before. But I would like to give a slightly different proof, which gives more than this estimate, which comes from the work of Nicolas Oresen. And so the other proof which will be useful is to write Hn equal 1 plus 1/3. It starts a little bit like the one which are there, but you take Hn over 2. So it's Hn that you divide by 2. So you have 1/2 plus 1 over 4 plus 1 over 2n. And if you take the difference between H2n, you see this goes to 2n and this one to 2n. So we take H2n and we remove Hn. What we get is 1 plus 1/3 plus 1 over 5. It's the same as here, but the difference is that we stopped at n and 2n. It's not an infinite series. And so we have at the end plus 1 over 2n minus 1. So excuse me, this is H2n minus Hn over 2. And so H2n minus Hn is 1 minus 1/2 plus 1/3 minus 1 over 4. You see, it's similar to that, but we have a finite sum, which is here. But when n tends to infinity, what you obtain at the limit is log 2. So H2n minus Hn is equivalent, it tends to log 2 when n tends to infinity. And this shows that Hn behaves like the logarithm of n. And this is something that Euler proved in 1731. which is the fact that hn minus log n has a limit when n tends to infinity, and this limit is the so-called Euler constant. Gamma is 0.577 and so on. This is Euler constant. It's a very interesting real number. Among the questions which are open concerning this number is whether this number is rational or not. The conjecture is that it is transcendental, so it is not a root of a polynomial with rational coefficients, but we do not know whether it's a rational number or not. And this is one of the main challenges that we are not able to solve. Euler proved that, and he proved something more. He proved that gamma, this Euler constant, is the sum for n equal to up to infinity of -1 to the n, zeta of m divided by n. So he proved that this series is convergent. The fact that it's a convergent series is not too difficult because it's an alternating series. And the limit is the limit of hn minus log n. So let me tell you how Euler proceeded. Euler used the expansion of the logarithm, which I mentioned before. It was proved by Nicolas Mercator in 1668, the logarithm of 1 minus x. And so he wrote the expansion of logarithm of 1 plus x, which is x minus x squared over 2 plus x cubed over x cubed equals 3 for x equal 1, 2, 3. No, it's 1 over, so x equal 1 over m, and m equal 1, 2, 3. We need that x is less than 1. We allow x equal 1 because we know the expansion of log 2. And so, what do you get? If you take x equal 1, you have the expansion of log 2 that we have seen. I write it 1 over 1 minus 1/2 of 1 over 1 square plus 1/3 1 over 1 cube, and so on. This is 1 minus 1/2 plus 1/3, but I prefer to write it like this, so that if I take m equal 2, I have the logarithm of 3/2, 1 plus 1/2, which is 1 over 2 minus 1 over 2, and here I have 1 over 2 square, plus 1 over 3, 1 over 2 cube, and so on. I take m equal, so here it's m equal 1, here it's m equal 2. Let me just write m equals 3. It is the logarithm of 4 over 3, which is 1 over cube, 1 over 3 minus 1/2, 1 over 3 square, plus 1/3, 1 over 3 cube, and so on. And you continue like this. And then what you do is that you add on the left-hand side, so you go up to log n, 1 plus 1 over n, so n plus 1 over n. You do the same, and you add. When you add, you see that you have log 2 plus log 3 minus log 2 plus log 4 minus log 3, and the other term which is remaining is logarithm of n plus 1. So you write the sum. What is the first term that you have? You have 1 plus 1/2 plus 1/3, so you get hn. What is the second term? You have 1/2 minus 1/2, and then you have the sum of 1 over n squared. which is zeta of p. And then you have plus 1/3 zeta of 3, and so on. And all these series converge. And this is an infinite series, which is nothing else than the series which is here. So there is some small work to be done to check that everything is convergent, which was not the main concern by Euler at that time, but it gives the formula which I wanted to prove. This Euler constant is related with the zeta function of Riemann in many ways. This is one way that it is related. Okay, so now I can come back to the zeta function, Riemann zeta function. And what I would like to explain is that the Riemann zeta function extends, so this is the main result which I will prove now. The Riemann zeta function extends to a meromorphic function in the plane. Meromorphic means that there will be one pole, and the pole will be at s equal 1. Riemann, in his memoir, does not speak of analytic continuation, but we will use the language saying that the following theorem, which is due to Riemann, the function zeta of s minus 1 over s minus 1. So I remove what will be the pole of zeta of s. The function zeta of s minus 1 over s minus 1 extends into an entire function in C. This means that there is an entire function in C, a function which has no singularity, it's analytic everywhere. There is a unique such entire function in C, such that if you take the real part of S greater than 1, then the value of this entire function is zeta of S minus 1 over S minus 1. The unicity is clear from the principle of analytic continuation. If you have two functions, the difference of which has zeros which are not isolated, then the function is 0. If you are working on C, for example, on a simply connected open set. And so the unicity is something which is well known from the theory of analytic function, but we want the existence. And this is a very interesting result, which was not considered by Euler, but this was due to Riemann. And Riemann, in his paper, not only proved this result, which is here, but he proved a number of results on this function. And he was especially interested in the zeros of the Riemann zeta function, zeta of S, or the zeros of the function which the zeros of the function zeta of S, so it's 1 over S minus 1 plus an entire function. And he studied the set of zeros. He proved that, we knew already that there is no zero. So let me try zeros of zeta. We already know that there is no zero with the real part of S greater than 1. This was proved using the infinite product. And Riemann obtained all the zeros of this function. Riemann determined all the zeros for real part of S, which is less than 0. And I will describe what are the zeros. These are called the trivial zeros. And so you see that there is a gap between 0 and 1 for the real part. And this is called the critical strip. Critical strip. It is 0, 7, the real part of S, even 1. Well, there is real part of S equal 1 and real part of S equal 0, which is remaining, but we will see that it was not proved by Riemann, but we will see that there is no 0 for the real part equal to 1. The proof is quite nice, and I will give it tomorrow. So the critical strip is this one. And what Riemann proved is that inside the critical strip, there are infinitely many zeros, which are called the non-trivial zeros. In the critical strip. This is what he proved. And now the Riemann hypothesis, which is open, is that all the non-trivial zeros, so the zeros of zeta of S in the critical strip all lie on the critical line which means the real part of S equal 1/2 in the middle of the strip. So the picture is the following. You have 0, you have 1, you have 1/2 in the middle. The Riemann zeta function is well known for the real part of S greater than 1 because of the infinite series and the infinite product. So here it's well known. Here it's well known, and we will see why it is well known. It's because there is a formula which relates zeta of S and zeta of 1 minus S. But inside the critical strip, it's much more mysterious, and this is the critical line here. And the hypothesis of Riemann is that all the zeros lie on the critical line. There are many partial results in this direction. For example, the fact that at least a positive proportion of the non-trivial zeros are there, but so far there is no proof. So I would like first to extend the Riemann zeta function into an entire function in C. This is the first thing that should be done. And for that, again, there are several proofs. In this theory, most results have several proofs. Even the prime number theorem has proofs using the Riemann zeta function and proofs which do not use a complex function theory. And so I will explain it by introducing the Dedekind eta function. Which is a function eta of S, which is the alternating sum, the sum for n greater than or equal to 1 of -1 to the n divided by n to the s. I take this in the domain of absolute convergence, which means I will take real part of S greater than 1. In this case, it is zeta of S is 1 plus 1 over 2 to the S plus 1 over 3 to the S. And eta of S is -1 for n equal 1 plus 1 over 2 to the S -1 over 3 to the S plus and so on. And so it's something which we already did before which is to take the difference z of s minus it of s. So what we do is that if we take z of s minus it of s, we have 1 plus 1, which is 2, and then 2 divided by 3 to the s. So it is 2 plus 2 divided by 3 to the s, plus 2 divided by 5 to the s. So we have the odd denominators with the exponent s and twice this. So if we look at the sum 1 plus 1 over 3 to the s plus 1 over 2n plus 1 to the s, which is what occurs here, we have twice this. So this is it of s minus it of s. And you see that we can write this is equal to 2. And we write the missing terms for zeta of s. So we will have zeta of s. And here, what is missing is, so we have added 1 over 2 to the s plus 1 over 4 to the s plus 1 over, okay, I shouldn't go too far, but okay, so and when you complete that, what you find, since I like to go a little bit further, we find that it of s, so the final result, is that it of s is equal to 1 minus 2, 1 minus s, and zeta of s. Okay, so this is what gives this simple computation. What do we get if we take s which tends to 1? If s tends to 1, we have it of s, which had the limit, which is minus 1 plus 1 over 2, minus 1 over 3, and we get again minus log 2. So eta of s has the limit, which is minus log 2, as s tends to 1. Zeta of s, we expect that we will get 1 over s minus 1, and so we look at 1 minus 2 to the 1 minus s. And for that, we have to remember what is 2 to the 1 minus s. In fact, I am not sure that I defined this, but when we write e to the s, by definition, it is exponential s log a. So, which means that if we write a to the s, we have to take a logarithm of a. But here we take just the logarithm of 2. So 2 to the 1 minus s is exponential 1 minus s log 2. S tends to 1, being greater than 1. And so 1 minus s tends to 0, and exponential 1 minus s tends to 1. And it is 1 plus 1 minus s log 2 plus a big O of 1 minus s squared. When s tends to 1, we see the expansion we have. And so if we take 1 minus 2 to the 1 minus s, we remove the 1 which is here, and we get s minus 1 log 2 plus a big O of 1 minus s squared. So it's equivalent to s minus 1 log 2. So this is log 2, this is s minus 1 log 2, and we deduced that s minus 1 zeta of s has a limit, which is 1. So 1 minus, no, s minus 1 zeta of s tends to 1 as s tends to 1. This is the first step, and we see that this makes some sense to say that zeta of s will have a pole of multiplicity 1 when s is equal to 1, which is coherent with what we want to prove. But we want to go further, and to prove more. And for that, we use a method which was used by Euler, but which was used also by Ramanujan, which is a method for accelerating the convergence of a series. And the idea is the following. We take the sequence AN is 1 over n to the s. And we take Bn equal An minus An plus 1. So the first term, S1, which is the it of S, it is A1 minus A2 plus A3 minus A4 plus and so on. And now we compare that with the second sum, which is the sum S2, which is B1 minus B2 plus B3 minus B4, and so on. A rather nice method of accelerating the convergence. What is S2? B1 is A1 minus A2. So this is B1. What is B2? It's A2 minus A3. And then B3 is, with the sign plus, A3 minus A4, and so on. So what do we get? We get A1, which is 11, and then it is again a kind of telescopic series. A2 occurs twice, so minus 2A2. A3 occurs twice with the plus sign, 2A, this was 2, 2A3, minus 2A4, and so on. So this is S2. So S2 is A1 minus 2. So we have A2, A3, so it is S1 minus A2. Okay, it is better to say that we have 2A2, so it is 2S1. Okay, maybe it's better to write it like this. The A1, I pretend that I have 2 A1. If I have 2 A1, I get S1. I get 2S1 minus A1. Okay, it's better to write it like this. So you see that S2 has a simple formula in terms of S1. The convergence of the absolute convergence of eta of S was obtained for the real part of S, which is greater than 1. But now what can we say for An minus An plus 1? It is Bn is 1 over n to the s minus 1 over n plus 1 to the s. This is Bn. You can write it as 1 over n plus 1 to the s times. So here you have n plus 1 to the s over n to the s minus 1. Okay, I will write n to the s. So n to the s, and so I have 1 minus n to the s divided by n plus 1 to the s. You see that the main term of n plus 1 to the s minus ns divided by n to the s plus 1. The main term is n to the s minus n to the s, which cancels, and the next term is n to the s minus 1. And so it's n plus 1 to the s. So this will be equivalent to n to 1 over n. And so we win 1 exponent n. But I want to make that a little bit more precise. And so we have to look at what is, it is 1 minus 1 over x s. And I want to see what happens when x, which is 1, so it's n plus 1 over n. So it's 1 plus 1 over n. So it's equivalent to 1 over n. X. Okay, so maybe I should better to look at my note. So the point is 1 plus 1 over n plus 1 to the s minus 1 to the s is exponential s logarithm of 1 minus 1 over n plus 1 is a classical logarithm of a positive real number. So it's equivalent to exponential s, and the logarithm of 1 plus 1 over n plus 1 is minus 1 over n. Minus s over n. And the exponential when n tends to infinity is equivalent to 1 minus s over n. And so we have to remove the 1, which is here, and therefore we find that the Bn is equivalent to 1 over n to the s plus 1. And here it is s, the s which comes from here. So maybe I write this. If I take for s a complex number. N to the s plus 1 is the same. The modulus is n to the real part of s plus 1. And so you see that we started with 1 over n to the s, and we have 1 over n to the s plus 1. And therefore, the series which is given by the Bn, which is the series S2, is convergent, absolutely convergent, for partial de S, for partial of S greater than 0. We started with 1 and we get 0. And so this proves the analytic continuation of zeta of S minus 1 over S minus 1. We have the analytic continuation for the real part of S greater than 0. We have removed the pole, which is S equal 1. And the same proof works to extend zeta of S minus 1 over S minus 1 in general for the real part of S greater than the given number. And so I sketch the proof. So we continue by induction. What we write is we define an0, which depends on S, as 1 over n to the S. And by induction, so this was my an before. The Bn will be an1. an1 will be an0 minus an plus 1, 0. And in general, we will define ank equal ank minus 1 minus an plus 1 k minus 1. And the same proof gives that ank is equivalent to s plus 1 s plus k minus 1 divided by n to the f plus k. And therefore, the series sum of A and K is absolutely convergent for the real part of S greater than k minus 1. And k is any positive integer. And by induction, we deduce that this is analytic function everywhere in all the plane. And the next result is that the series SK, which is the series which is here, SK, we have to take the sign -1 to the n, the sum for n, because we take each time alternating series. And so this we have by induction that sk is equal to 2 sk minus 1 minus a. So it's a1 to the k minus 1. It's and so this proves that the Riemann zeta function is extends into a non-time function in all the planes. Okay, so this is one proof of the analytic continuation. I thought I would be able to prove other results on the Riemann zeta function, but I am afraid that the time is over. So I will continue tomorrow. What I thought I would do now is to give a formula for zeta of 2. I will give an infinite product for the sine function, and I will explain some integral formula for the values of the zeta function. And after that, I will give a survey of the results without going so much into the proofs of the different results. So thank you for attending this first course, and I continue tomorrow at the same time. Thank you.
Thank you. Thank you, Lasky. And also thank you using wearing 2020 t-shirt that Simba school.
Yes, for the t-shirt.
Yeah, that t-shirt. We can see you clearly. Okay, maybe any question before we? Yeah, I think because if we want to prove everything, I think we will not have time. So yeah, I think when we already get some, yeah, at least we know some properties of Riemann zeta function. Okay, I think no, that one already mentioned. Actually, there is one in chat, but that one is a little correction.
Okay, I can try to find the chat.
No, I mean that one is only a little correction because we know there is some missing thing, but it should be fine. Yeah, we know.
Yes, probably you're right. Yes.
Yes.
I think it's okay. Yeah. So thank you for the correction.
Yeah, but we know the correct one. Should
Yes.
be fine.
I've been surprised that there is no misprint in my lecture. Okay.
Yes. Okay, maybe. Yeah, I think that's all for today. So thank you very much, Professor Michel Waldschmidt, and see you again tomorrow.
Okay, thank you.
Okay, I think since there is no question, I think we can end our today's session. So yeah, see you again tomorrow. Thank you, everyone. Thank you. Goodbye.
Bye.